All of you sure? That side? Yeah. You see this? Okay. So just a brief review of what we did in the last talk. Since we have to move from special theory of relativity to general theory of relativity, so just a brief review. It was there's something called the principle of relativity, which is not new. With this idea was there even in Newton's time. It's called principle of relativity. Principle of relativity. Now, the principle of relativity, it states that the laws of physics. You will be standing for
that's all.
The laws of physics are the same relative to all the observers. Like whether you are staying still, whether you are at rest, or you are moving, the law of physics is the same. For example, F equals ma. So if someone staying at rest writes the law F equals ma, the moving observer will have his coordinates will be primed, like F prime is equal to ma primes, but the law will be the same. F prime equals ma prime. So the principle of relativity says that the form of the law is invariant. It should not change. It should be the same. And it makes sense. How useful a law would be if it is not the same for all the observers. It has to be the same. It has to be a universal law. So that's the principle of relativity. Whether you are staying still, whether you're moving, the law is the same for you. How are we going to test this? We consider two observers, observer O and observer O prime. Both are observing an event that is taking place here. I should add here time as well. An event is taking place at a location. The location of the coordinates relative to this observer are x, y, z, and it's taking place at some time t. So these are the coordinates of this event relative to the observer O. And coordinates of this event relative to observer O prime are x prime, y prime, z prime, and let's be assuming it to begin with. We're just assuming that this time is, let's take it to be different initially, right? So the coordinates of this event are x prime, y prime, z prime, 3 space coordinates and 1 time coordinate, and we're assuming that this time is different from that time, right? Okay. In general. So what is the transformation between these two sets of coordinates? Very simple. Transformation is, it's not there?
What do you think?
I'm going to write it anyway, so I'm going to write it anyway. But it's good that we have it there as well. Galilean transformation. So that's pretty simple. How are the coordinates x prime and y prime, x prime and x of this point related? Very simple. Suppose if this observer O is moving, look, according to the diagram, look, this observer O prime is moving with speed v, with velocity v relative to observer O. You may assume that observer O is at rest and observer O prime is moving with a velocity v in the forward direction. To make things simple at the start, we are assuming that this motion is taking place only along what? Along the, let me just write x coordinates, along the x-axis. So that's x, x, y, and z. X prime, y prime, and z prime. Right? Okay. Now this frame is moving with speed v relative to the first. So observer O prime is moving with a constant velocity v relative to observer O only along the x-axis. Right? To begin with, we keep it simple, but the idea is the same. Even if you consider general motion, the physics won't be different. Okay, so what would be the transformation between these two coordinates? How is x prime related to x? Simple. X prime is simply this distance. X prime is from here to the event. That's it, x prime. Whereas x is what? X is the entire distance from the origin of O to this prime. So how are these distances related? This entire distance and this distance. Obviously, this distance, which is x prime, is this entire distance minus what?
Vt.
Minus Vt. The entire distance is x. If from this entire distance x you take away this Vt, what do you get?
X prime.
X prime. So it's simple. X prime is simply x prime equals x minus Vt. And y, and since I'm only considering motion along the x-axis, y prime is equal to y, and z prime equals z. And so what about t prime and t? That is the most crucial point in all of relativity. Do I take t prime as the same as t? Do the time measurements by observer O prime and observer O are different or same? Galileo assumed that time would be the same. The time, whether you're moving or whether you're standing still, the time interval that you measure will be the same. The ticking of this clock is at the same rate as the ticking of that clock. So this is what their assumption was. They assumed that t prime is the same as t. Do I have, yeah, you can see there, can all you see there? X prime equals x minus Vt, y prime equals y, z prime equals z, t prime equals t. It was their assumption. They assumed that t prime is equal to t, right? Okay. So everything was okay from Newton's time until the mid of the 19th century. In fact, late 19th century, not mid 19th, late 19th century. It was about 1885 when two gentlemen, American gentlemen, Michelson and Morley. But before I talk about Michelson and Morley, let me explain to you what this leads to. Now, suppose that this transformation is correct. It seems, apparently it makes sense, right? It is common sense, right? Okay. So, suppose that this particle, this event is just a particle, right? And it is moving with the speed u prime relative to this observer and with the speed u relative to that observer. So what will be the connection between u prime and u? According to this transformation, the connection would be u prime equals u minus v, or u equals u prime plus v. This transformation equation, the Galilean transformation, leads to this formula which is called velocity addition formula. Now what it simply says is, which again, common sense, that if this frame, like a train is moving with speed v relative, you are standing on a platform, right? So you are observer O, you are standing on a platform. So relative to you, a train is moving with the speed v, and inside the train, something is moving at speed u. So what would be the speed of that object relative to u? The speed of the train plus the speed of that object, v plus u. So this is what this is what these transformations lead to. These transformations say that if there is an object moving with speed u inside the train, and the train itself is moving with speed v, relative to the outside observer, the speed of that particle would be u plus v. This is called the velocity addition formula. Now imagine this particle is light signal. It's a light signal. And light signal are, we represent the speed of light by what? C, small letter c. So what if this is c? If this is c, right, small c. It means this will be c prime, c, which means this is c, and that is c prime. So it means that if the speed of the particle is c, inside this frame. The speed of this light signal will be c plus v relative to the observer outside. It means greater than the speed of light. Common sense? That if the light has speed c relative to this observer, and the observer himself is moving at speed v, relative to the outside observer, this light signal is moving at c plus v, the speed of the light signal plus the speed of the train. Right? Okay. That seemed common sense to everyone until this experiment was performed in 1885 by two Americans, Michelson and Morley. And that changed everything. Michelson and Morley performed this experiment to measure the speed of light in vacuum from a moving frame. See, in two different directions. You know that the Earth is moving, right? Earth is moving with some speed. So if we measure the speed of light signal coming from above and coming from the front, according to this velocity addition formula, U plus E, that will be different. For example, if this Earth is moving at speed v, and the light signal moves with speed c in vacuum, what would be its velocity relative to us? C plus v. And if light signal coming from there, it should be c, because its velocity is taking place along the x-axis. So if any signal is coming from there, this v should not add to that. But it will add to any light signal that is coming from the front. So according to Galilean transformation, or the Galilean velocity addition formula, the speeds of those two light signals will be different as measured by us. Because for the light signal that's coming from the front, we are also moving toward it, so our velocity should add to it. So it means we should measure c plus v, and for the light signal coming from up there, we should measure what? C. But when Michelson and Morley performed the experiment, thousands of times they got c for both. Which means what? That and this from that time, this experiment has been performed thousands of times with the same result. So there's no doubt about this experiment now. This shows what? That the speed of light in vacuum, not in a medium, speed of light in vacuum is a constant regardless of the motion of the source or the observer. Whether the observer moves towards the light signal, whether the observer moves away from the light signal, whether the source is moving toward you, whether the source is moving away from you, the speed of the light signal, provided it's traveling with the speed of light. Speed of light in vacuum is constant regardless of the motion of the source of the observer. Is it in contradiction with Galilean transformation? Which say that the speed of light, that light signal should be c plus v, and that should be c. So it means if Michelson-Morley experiment is correct, which it is, if Michelson-Morley experiment is correct, Michelson-Morley experiment is correct, then this cannot be correct, right? Okay. So, but it was very hard for people to believe that this could be correct. This could be incorrect. They thought this can never be incorrect, except for Einstein. Everyone thought that this was correct. There's some problem somewhere. Some problem somewhere, maybe in the experiment, maybe somewhere else, maybe in the principle of relativity. They were ready to give up principle of relativity for this. But it was only Einstein, a 25-year-old clerk working in a patent office. He was a clerk at that time. He wasn't a scientist. He was just a clerk working in the patent office in Switzerland, right? And people like Lorentz and Planck and giants of physics, they were not ready to give this up. They said no, this cannot be incorrect. Maybe the principle of relativity is incorrect. But it was only Einstein who realized it. Only Einstein believed that principle of relativity cannot be incorrect. And Michelson-Morley experiment was correct. Throw this away. And to think out of the box and to make such bold assumptions need people like Einstein. So, and at that early age, right, 25, he said against all the physicists and the top physicists at the time, he was on one side, the rest of the world was on the other side. So he said, throw this away, find another squared transformation, right? Which will give you C for both the observers, which means that you should find a transformation, throw this away, find a new transformation, and the new transformation should give you a velocity addition formula which shows that C is the same for all the observers. Let me just tell you what the correct velocity addition formula is in fact. Okay, the correct velocity addition formula is this. U equals U prime plus V over 1 minus V squared over, no sorry, not V squared, V C and 1 plus, I'm sorry, VC over C squared. That's the correct. How do I know this is correct? This will give you C for both observers. Suppose this U prime speed is C. So it means this will be, sorry, I'm sorry, not V. This will be U prime, sorry. U prime. This is U prime. Okay. So suppose, okay. So suppose this speed of the particle in that frame is C. So it means I replace the U prime by what? C. This goes away, right? Here take the common denominator, the LCM. C plus V over what? What do you get? C plus V over C? C plus V over C. What is this equal to?
C.
C. So you see? So it means this is the correct velocity addition formula. So find out the transformation which gives you this velocity addition formula, right? Lorentz transformation. Oh, that's, yeah. But it's not written in a very suggestive way. I'll have to write it again. I think, yeah, that one, this one. This one, thank you. Okay. So the correct transformation, this is one point. See, if Galilean transformation is correct, like x prime equals x minus vt, y prime equals y, z prime equals z, and t prime equals t, the most crucial thing, then you know that if you have to test the principle of relativity, principle of relativity says every law, any law is the same for all the observers. And you know that every law is written in terms of equations. And the equation contains scalars or vectors. Suppose there's a vector equation like f equals ma, right? There's a vector equation. So if I have to check whether that law is invariant, is the same for both the observers, I'll have to do this transformation, right? Now the law, let's say f equals ma, and you know that these are vectors. That's the crucial point. That will explain why we live in space-time and not in space, right? Can all you see that? Okay. So let's say f equals ma. Now, the f is a vector, a is a vector, and they have components. If we live in 3D, each vector, f and a, will have how many components? 3 components. Vectors have 3 components in 3D, right? Okay. So it will have 3 components, fx, fy, fz. And a will have 3 components, ax, ay, ez. Now the question is, do we need the 4th component if this transformation is correct? Now let me change the scenario a bit. Suppose if this motion is not along the x-axis, it's general motion. What change will you see here? This y prime won't be equal to y, z prime won't be equal to z. So it means they will also change. But what about t? If Galilean assumption was that t prime is always equal to t. So it means if I consider a general form of motion, a general transformation, these coordinates will change. So I will have to check whether my fx is changing the right way, whether my fy is changing the right way, whether my fz is changing the right way. But do I have any doubt I don't need to have this fourth component in my vectors because I don't have to check it. All of you with me? I don't need the fourth component. Why? Because I know that it won't change. So I don't have to check it. So if I don't have to check it, then it means I don't need it because I know that the fourth component, if it existed, it will be the same, so I don't have to check it. So I don't need it because if this doesn't change and I don't have to check it, I don't need it, right? But as you know that the experiment, Michelson-Morley experiment has clearly demonstrated that this is not a correct transformation. And what Einstein did was he obtained the correct transformation law in order a transformation law that will give the correct velocity addition formula. And the correct velocity addition formula is u equals u prime plus v over what? Over 1 plus vc over c squared. So what Einstein did was he derived the correct transformation between the coordinates x prime, y prime, z prime, x, y, z, which will give us this thing. And that correct transformation was this. The other form that I just said.
That's not loading up.
Oh, this one, yeah, this one. So this is what the correct transformation was. You see here in this, not only the x, and you know what, y prime equals y, z prime equals z, depends on whether the motion is along the x-axis or not. Suppose if there is general motion, then obviously y prime won't be equal to y, z prime won't be equal to z. So these will change. But what's the crucial change now? What's the crucial change now? That t prime is not equal to t. That is the huge step. That is the main difference. In the Galilean point of view and the Einsteinian point of view. That t prime is not equal to t, and now that is experimentally proven, because if t prime was equal to t, then the Galilean velocity addition formula would be correct. But we have just found that Michelson-Morley experiment shows the Galilean velocity transformation, velocity addition formula is incorrect, which means the Galilean transformation is incorrect. But why are these transformations now correct? Because they give us this velocity addition formula. I don't have time to demonstrate that how we go from this to this, but you can take my word for this, that those transformations will give you this velocity addition formula. So this velocity addition formula, these transformations are in line with what? Michelson-Morley experiment. So Michelson-Morley experiment shows that this formula, these transformations are correct. So now we know that these transformations are correct because they give you this velocity addition formula, which in turn shows you that the speed of light is constant regardless of. I just showed that if you put c here, you will get c. So both observers will see the light signal moving at the same speed, right? So now it is established that this transformation law is correct and not the Galilean one, right? But the reason is at low speeds we can still use Galilean transformation because you look at see if this v is much smaller than c, do you get Galilean again? But if v is negligible compared to c, won't this factor be 0? And that factor up there will be 0, and this factor will be 0. Will you get Galilean transformation again? So it means in the limit of low velocity, Lorentz transformation reduced to Galilean transformation. So it means at low speeds, when the speed is much smaller compared to the speed of light, you can still use Galilean transformation. You can still use Newton's laws, Galilean ideas, everything. And this is exactly what we do. We haven't thrown away Newton's laws. We still use them because when v is negligible compared to c, this transformation law will reduce to what? To the Galilean one. So it means for low speeds you can use Galilean, but not at high speeds. If you're studying phenomena like particles moving and particle accelerators, of course this will be the correct transformation, right? Okay. So now, if this is the correct transformation, now that's the crucial idea. If this is the correct transformation, and now you are writing a vector equation representing some law, will the fourth component matter now? Will you have to check the fourth transformation of the fourth component as well? You will have to, of course, you will have to check x, y, z component. Let's say you are writing in some equation, suppose you're writing a formula s equal to ut or something, right? Any formula involving displacement, right? And a formula involving velocity. We know that we have to check whether this law is correct. We'll have to check whether the components of s and component u transform like this. Okay, how many components do I need to check now? Because I'm not sure about the t component now. So it means I'll have to check what? XYZ components, how they transform, whether they transform like this or not. But now do I need the fourth component to check? Because the fourth component is also changing. So it means the vector has to have a fourth component. And I'll have to see whether the fourth component varies like this, transforms like this. Otherwise this law won't be correct. So now, if Lorentz transformations are correct, which they are, you know, according to Michelson-Morley experiment. So it means any vector equation that you write, any physical law that you write, involving vectors will have what? How many components? Four components. So it means the displacement has how many components? 4. 3 space component, 1 time component. Velocities have how many components? 3 space component, 1 time component. Acceleration? 3 space component, 1 time component. Force? 3 space component, 1 time component. So it means the vectors that describe the world, the universe, have 4 components. The displacement, you know, why do we normally say that we live in three dimensions? Because the displacement that we write has how many components? 3 components. Therefore we say, since the displacement in the universe has 3 components, the universe is 3-dimensional. But now we've discovered what? Our displacement has how many components? Otherwise it won't, if it's only 3 components, it won't be Lorentz invariant. Right? So in order to be Lorentz invariant, the displacement has to have how many components? 4 components. So it means the world we live in, the universe we live in, has the displacement that has 4 components. Three space components and 1 time component. It means we live in 4-dimensional. We don't live in space. We live in what? Space-time. Is this point clear, or any problem with this? Any questions about this? Crystal clear at this point?
Yes.
We live in space-time. You agree? Okay. So now we can proceed now from here. Sure. Okay, so this was, sorry I took so much of time because this was the thing that I did, because I have to make the connection, right? Otherwise it will be pointless. Now I can proceed with the general relativity. So this is special relativity. Right? Yeah.
I'm just saying that when Tarski space is wrong, like space is actually 4D now. I don't know, I read somewhere that they can prove that instead of 3D plus D, it's now just 4D, because otherwise it's going to go against.
You know what? After this theory, people have come up with numerous ideas, not just the one that you were talking about. So see, you can come up with anything, but unless you establish this experimentally, it's fruitless. So people have come up with many other theories, alternate theories, right? But they haven't been able to demonstrate it experimentally. If anyone can demonstrate, you know, what Einstein said, that no number of experiments can prove my theory for sure, but a single experiment can disprove my theory. If you come up with a single experiment that disproves it, theory is gone. So if you come up with a theory, any single experiment that contradicts the Einstein theories, and Einstein will be gone. Then we can consider new theories, and then we will have to see whether they corroborate with the experiments or not, right? Okay. So this was the idea. So now we know that we live in 4 dimensions. Our vectors will have how many components? 4 components. Our displacement has 4 components. Our velocity has 4 components. This is called a 4 velocity now. 4 velocity, because it has 4 components. 3 space components, 1 time component. Otherwise it cannot be a direct velocity. Otherwise it won't be invariant under Lorentz transformation. Right? Okay. So the velocities are now 4 velocities. The accelerations are now 4 accelerations. And this is how we write them. The velocity is now written as, it's called a 4 velocity, and it's written as Vx, Vy, Vz, and Vt. There's a 4th component. But in relativity, the relativists write it like this. They write this one first, and they represent it as a V0. V0 and V1, V2, and V3. And they write this first. Yeah, right? It doesn't make a difference, right? And what about the acceleration? The acceleration no longer your 3 acceleration, it's a 4 acceleration. So acceleration will be a 4 acceleration. Again, ax, ay, az, and what? At. Now I will come back to this later to show that if these 3 have a positive sign, that one will have a negative. So for the time component is the opposite sign of the space component. You may have all these a positive and that as negative, or all these three as negative and this one as positive. I'll come back to that point later. Okay? Okay. So now it means the acceleration, your acceleration has to be a 4 acceleration. Your velocity will have to be a 4 velocity. Displacement is 4 displacement. And a 4 force, 4 force. Right? All have 4 components. Now, when Einstein finalized the special theory of relativity, he immediately saw that Newton's law of gravity. How many second year students? Raise your hand, please. Second year students. How many? That's it? Okay. So he immediately saw that Newton's law of gravitation, F equals G M over R squared. This is Newton's law of gravity. This cannot be correct. Although we will still apply it if within its domain it will be applicable, but in general it's not true. Why? There are 2 reasons. First of all, this vector involved has how many components? And this is, if I write in a vector equation, then there has to be a vector here as well, so this is a unit vector. But don't worry about this at the moment. Okay, so first of all, in Newton's law of gravity, how many components does it have? 3, right? So you can say, oh, it's simple, just find a 4th component for this one, and the law will be true. Just find a t, it already has 3 components, fx, fy, fz, just find a 4th component, ft, and everything will be okay. No, everything won't be okay still. Why? You know the reason. The reason is this. Lorentz transformation and also the Michelson-Morley experiment, they show that nothing can go faster than light. The maximum speed that you can have is c. If you try to add something, it still comes out to be c. So nothing can go faster than light. Even a signal cannot go faster than light. Otherwise, relativity will collapse. Right? So unless you collapse relativity by showing an experiment that relativity is not true, relativity is true. Therefore, even experiments show that nothing can exceed the speed of light. Now, even an interaction cannot exceed the speed of light. Interaction between 2 objects. Now, what this suggests is that suppose if there is, let's say, one planet, or some other planet, or some other star, or something, right? Some other object here, and there is a gravitational force existing between them, and they're far apart. Like suppose they're 2 different galaxies, billions of light years away. 2 different galaxies, or 2 different stars, billions of light years away. What this law says is that there's a force between them. Right? There's a force between them. If you, according to this law, if you change the distance between them, like moving this object away, what will happen to this force? Force will change instantly, or it will take some time. According to this formula. According to the formula, instantly. This shows that if you distance between 2 galaxies are billions of light years apart, and the distance between them changes, the force between them will change instantly. So it means this law is allowing instantaneous propagation of the signal, and instantaneous propagation means infinite speed. Is that allowed? According to Michelson-Morley experiment, relativity? No. So it means if special relativity is correct, which it is, then this cannot hold. This has to be changed. And this is what Einstein said to, in 1905 we got a special theory of relativity, and he immediately realized that this is incorrect, and his next step was to get a correct law of gravitation. And as you've just seen, that it won't be as straightforward as just finding a 4th component for this 4th and the 4th component for that vector. No, it won't work this way. Because it suggests instantaneous action, which is against special theory of relativity. So this has to be changed. And Einstein started in 1905, and then for some years he tried, and then he stopped, and then he started working for working in quantum mechanics. So 3 years he worked for quantum mechanics. Then in 1911 he came back. Right? He tried from 1905 until 1907. He couldn't succeed, and then from 1907 he got interested in quantum theory. So for the next 3 years he worked in quantum theory, and then 1911 he came back to this question again. Right? Okay. So now I have to show that Einstein realized that gravitation is not a force. Gravitation is a manifestation of curvature of what? space-time, not space. We just realized special theory of relativity has shown us that we live in space-time. Our displacements have 4 components. It's a 4 displacement. Our velocities are 4 velocities, our accelerations are 4 accelerations. So it means we live in a space-time. So how did Einstein arrive at this is basically the topic of today's talk. How did Einstein arrive at the concept that, what is the time?
2:40.
Sorry?
2:40.
I can go till 3:30, yeah, that's enough. Okay, so how did Einstein arrive at the idea that gravitation is a manifestation of space-time? So he first showed that in the presence of a massive object, like in the presence of gravity of that massive object, the space-time around a massive object cannot be flat. It has to be curved. This is what I have to show today. That the space-time around a mass cannot be flat. So before I discuss this idea, let me just talk about curvature for a moment. I just take an aside to talk about curvature. Now, curvatures are of 2 types: extrinsic curvature and intrinsic curvature. What's an extrinsic curvature and intrinsic curvature? Now, surface of a cylinder looks like what? Curved? You know what is actually not curved, it's flat. How? It has an extrinsic curvature that you can see. The curvature that you see when you're outside that surface, right? The apparent curvature, that is extrinsic curvature. But there's something called intrinsic curvature as well. How do we find the intrinsic curvature? Now, intrinsic curvature can be found by staying on that surface. Suppose if you were living in a space or living in a space-time and you want to know whether the space-time is curved or flat, you can do something, right? You don't have to go outside, because if you go outside you will see an extrinsic curvature. But how do you find the intrinsic curvature? Now, it's simple geometry. You know that if I draw a triangle on a flat surface, the 3 angles add up to what? 180 degree, right? Okay. This is a property of flat surface. Parallel lines do not meet, and so on. And if I draw a 4-sided figure in such a way that 2 of the sides are parallel, now that's good. 2 of the sides are parallel, they're congruent, they're parallel and they're equal. They're parallel and they're equal. What can you say about these 2 sides? If these 2 sides are parallel and equal, what do you say about these 2 sides? Parallel and equal. They will be equal. Right? So this is the property of flat space. Flat surfaces. Now, suppose if I make this triangle on a piece of flat paper and make this diagram on a piece of flat paper, and then I roll it in, and then I roll it and make it a cylinder. So before I rolled it, before it was a flat paper, it was obeying the laws of flat geometry. The sum of the 3 angles is equal to what? 180 degree. So if I can roll it into a cylinder, if the angles will still add up to 180 degrees. So it means this law that the sum of the angles of a triangle is what? 180 will still hold on what? The surface of the cylinder. So it means surface of the cylinder does not contradict the rules of geometry. Basically, these are called Euclidean. This is called Euclidean geometry. Euclidean geometry is a flat geometry, according to which sum of these 3 angles will be what? Equal to 180 degree, right? So it means this rule will still be valid if I just draw the triangle on a piece of paper and roll it into a cylinder, right? So it means the angles will still add up to 180 degrees. So it means although surface of a cylinder looks curved, it has an extrinsic curvature, it does not have an intrinsic curvature, because the laws of Euclidean geometry still hold on the surface of curvature. But that won't be the case on the surface of a sphere. If you draw a triangle on the surface of a sphere, the angles won't add up to 180 degrees.
What about the Earth?
Anything which is, Earth is a curved surface. It has an intrinsic as well as extrinsic curvature. But the cylinder has extrinsic curvature, no intrinsic curvature. But sphere?
Sphere has intrinsic.
Both extrinsic as well as intrinsic curvature. Paper, into a cylinder, so that everything will be preserved. All the laws, if I draw a triangle here, everything will be preserved. I can easily roll it into a cylinder. Can I roll a piece of paper into a sphere? No. So it means if a flat surface can be rolled in easily without any cutting, if it can be rolled into a curved surface, that curved surface actually is intrinsically flat and extrinsically curved, but actually intrinsically flat. But since I cannot roll this into what? A surface of a sphere, can I? No. Conversely, I can roll back a cylinder into what? What? A flat surface. Can I do this with the surface of a sphere without cutting? I cannot. So that is the basic distinction between surfaces that have an intrinsic curvature and the surfaces that don't have an intrinsic curvature. That you can, if a surface has an intrinsic curvature, it cannot be rolled into a flat piece of paper without cutting, like a surface of sphere. But if it can be rolled, it means it does not have an intrinsic curvature, right? So what Einstein's theory talks about, the curvature that the Einstein's theory talks about, is not the extrinsic curvature. It's what? What? The intrinsic curvature, which can be determined by drawing like triangles in the space and adding the angles to find whether if they add up to 180 degrees, the surface will be flat. If they don't add up to 180 degrees, it means what? They will be. The surface is curved. It has an intrinsic curvature. So that is the idea that we're going to talk about. So I will. Yeah, you can see that. When they say positive curvature, negative curvature, flat curvature means no curvature, right? So what they're talking about is the intrinsic curvature, not the extrinsic curvature. Is that clear? Right? Okay. So I will come back to the curvature thing in the end, right? Now, what was the Einstein? So now you have the idea of intrinsic and extrinsic. Now we can proceed and see the line of reasoning of Einstein. How did he arrive at the idea that space-time is, the space-time in the presence of a mass must be curved, right? Okay. I started with special relativity to show that Newton's law of gravity cannot be correct. So we have established that the law that you studied in your A2, it's not correct, but will still hold for under certain circumstances that are not outside this. Suppose if you're studying phenomena taking place at low speeds, and in solar system, for example, it will be okay to apply F equals mv over r squared. So NASA people are all the time applying it, right? But if you're trying to study a black hole, so space-time near a black hole or space-time near a neutron star, Newton's law of gravity won't work, right? Okay. So how did Einstein arrive at the concept that gravitation is not a force, but it's what? The curvature of space-time. The space-time around a mass has to be curved. Okay. This starts with Einstein's equivalence principle. EEP. Einstein's equivalence principle. People give it in different forms: strong equivalence principle and weak equivalence principle, and so on and so forth. But I'll just talk about equivalence principle, whichever form, right? Okay. Actually, I'm using the weak form of equivalence principle at the moment, because that's enough for you, the weak form. You don't need the strong form at the moment. So equivalence principle. And what is equivalence principle? It's a very simple idea. What it says is that in a limited region of space-time, there is no distinction between, consider two frames. One, which is lying in a gravitational field, in a uniform gravitational field. Let's say it's on the Earth, right? This is on the Earth, right? So it's in there's a gravitational force acting on it, right? If we consider that it's a force at the moment. So it's in a gravitational field, right? It's in a gravitational field. And the other frame of reference is in outer space where there's no gravity. And let's say this is Earth's gravity, so let's make this A equal to G, right? And another frame of reference, which is in outer space, where there is no gravity. Suppose if this frame is at rest or is moving with uniform velocity, what would be the situation inside? Will this person be standing still or be floating or what? Floating? In fact, everything is floating, right? Everything here in this frame. But things will suddenly change So it means this person won't feel any gravity. They'll be floating. Everything will be floating, right? So if what if the person drops a pen? What happens to the pen? It will stay there. It will stay there, right? Okay. So he can clearly see that there is no gravity. But things dramatically change when this. Is it on? Can you just turn on the fan as well, please, Mustafa?
So that might mess with the audio of the recording.
Okay. It's okay. Come.
Maybe.
Thank you.
I think this one is on that one.
Let's move to the side.
No, I think that one is on. Sorry.
That one not on.
It is on this one. Sure. Right.
Viewers, just go ahead. Almost on.
It's on?
It is on.
Anyway. So,
No. Wait, now just turn on
I feel the difference here. Okay, so everything will be floating here, and the person inside will feel that there's no gravity. It's floating, right? No gravity. But what if this frame, let's say there are jets, right? And jets are fired backwards, right, and downwards, and now it has an acceleration A, which is exactly equal to G, 9.81 meter per second squared. What will happen inside this frame now? Now what if we drop something? It will fall just as it falls in a gravitational field. And will it now feel his weight now? He will. So Einstein's equivalence principle says that in a limited region of space-time, in a limited region, if it's not limited, then of course he will see the difference. Well, he says that in a limited region of space, and that limited region can be huge, right? So don't be misled by the term limited region. So what he says is limited region of space-time, these two frames are indistinguishable. That's the person inside won't be able to tell whether he's inside a frame which is accelerating upwards with acceleration 9.81 meters per second squared, or whether he's at rest inside a gravitational field. He was 100% convinced about this fact, Einstein, and this is what led to general relativity. This is what led to curvature of space-time. This principle. We call principle of equivalence, right? Principle of equivalence, right? In equivalence principle or principle of equivalence, right? Okay. So, assuming that this is true, and it is true, in a limited region of space-time, you won't be able to tell the difference. Only if this is like huge, maybe thousands of kilometers, then you will start seeing the difference. But obviously, in a limited region, you won't see the difference. So, if it's a limited region like this room, the person inside won't be able to tell whether it's, right now we don't know whether we are at rest in a gravitational field or we are accelerating in outer space with no difference whatsoever. Which means that if you perform any experiment inside here, it will give exactly the same results as any experiment performed on the surface of the Earth, right? So no experiment is.
So why limited? Why wouldn't it extend to that?
Okay, I tell you what. Why limited? Now, what will happen in this frame if you drop two objects? They'll go parallel. They won't. They will go parallel, right? If I drop two objects here, right? So how will they fall? Parallel. Even if this is extended, thousands of kilometers, one object drop at one corner, the other drop at the other corner, they will still fall parallel. But it won't be the case here. If this is not limited and this is extended, like this frame of reference is extended, and you know the Earth attracts everything toward the center according to Newton. What you'll see is if you drop something here and you drop something here, they won't be parallel. They will start coming closer and closer and closer. So you will see the difference in that case. And you will tell, oh, I'm in a gravitational field, I'm not accelerating. So there has to be a limited region of space-time, right? And that limited could be very large. It could be kilometers, could be hundreds of kilometers. In fact. Okay. So that's one thing, equivalence principle. So the two frames of reference are exactly similar, no difference. Okay. The other idea is different rates of clocks in an accelerated frame of reference. How many of you have watched the movie Interstellar? So we must have, all of you must have seen the different rates of clock in different gravitational fields, right? If the field is very strong, the rate of the clock will be very slow, right? Okay. So let's first talk about, and now you will see why Einstein came to the conclusion that time runs at different rates. Clocks run at different rates in what? In a gravity. If the clocks are lying at different heights, they will run at different rates. How did Einstein arrive at this conclusion, right? Okay, and this will lead to curvature of space-time in the end, right? Okay, so let's first consider two clocks at different points in an accelerating rocket. Suppose there's an accelerating rocket which is accelerating upwards, right? And there are two clocks. Let me show it with different colors. Right? These are the two clocks. So, and they are inside a rocket, and the rocket is accelerating upwards. So the rocket is accelerating upwards. A. Now, suppose at this instant, this clock, someone is sitting there, right? Operating this clock, and someone is sitting here operating that clock, and they can communicate. They can talk, right? Okay. He shouts and he can hear. Okay, so let's say at this instant, a light signal is emitted by this clock at this instant. Light signal is emitted by this clock. Right? Okay. At this instant, someone is operating this clock. Someone is here. And the person shouts, I'm sending the light signal. I'm going to send light signals at an interval of 1 second by my clock. Each 1 second interval, I'm going to send a signal. Right? Okay. Now, rocket is accelerating upwards. When this light signal is emitted, this clock is accelerating upwards. Where will this clock, if it is acceleration this time, where will this clock receive the signal? If it is accelerating, up there, right? So that's the final position of the clock when it receives this signal. And that's the final position of the... Now this person is shouting, I'm sending the signal at 1 second intervals. Will he believe? Why not?
Maybe that's the same.
This is when the signal is emitted, this clock is accelerating upwards. This clock will receive that signal before 1 second by this clock. He's sending signals at 1 second intervals by his clock. But the other one, let's say this person is A and that person is B. So A shouts that I'm sending signals at 1 second interval by my clock. But B will receive that signal before 1 second has elapsed by his clock. What will he conclude?
That is,
Let's say A says, I sent the signals at 1 second interval, and what he finds is that he received the signal at 0.6 second intervals because he's accelerating upward. So he will say, oh, his 1 second is actually, by my clock, is 0.6 seconds. So he will shout, it's 0.6 seconds. He will say, no, it's 1 second. Your clock is running slower. Get this, all of you? Is this point clear? Well, that explains what. Any questions? Shan, clear? Are you sure? No, you don't look. 100%? You kind of lost?
But sir,
Yes.
if this light is constant for all observers, then why will different
He's not moving with constant velocity.
like aren't
No,
they
speed of
both-
light is the same. The speed of light hasn't changed. It's because he has accelerated. It's not saying that the speed of light I'm measuring is different. What he's saying is the interval between signals is different.
But both
Not
of
the-
them are accelerating at the same rate.
Yeah, but the problem is if they were going with constant velocity, then there wouldn't be any different.
Yeah.
When this leaves, when the light signal leaves is no longer part of this accelerating rocket. And in the meantime, this accelerates upwards. So this observer is going to receive it. So what will be the conclusion? The person A says what? I'm sending signals at what? 1 second intervals. What is it? No, you're lying. You're sending signals at 0.6 second intervals. They would say, no, your clock is running. No. If I say 1 second is elapsed, and that one says, no, 0.6 seconds elapsed. So what do I conclude? If I'm A, what do I conclude? Oh, your clock is running slower, right? Okay. Einstein said that if this happens inside an accelerated frame of reference, and you know the limited region of space-time, accelerated frame of reference is exactly equivalent to what?
Gravity.
A frame of reference sitting at rest in a gravitational field. So what he said was that I believe in equivalence principle. No experiment inside accelerated frame of reference can tell me the difference between an accelerated frame of reference and a frame of reference sitting at rest on the gravitational field. So he would say that we should get exactly the same result inside what? Okay. Why should we believe Einstein? No. Why should we believe Einstein? See, there is no written proof of this fact. It's Einstein's intuition. The only test is experiment. Experiments show that Einstein is right. So as long as experiments show Einstein is right, we accept it. Einstein says, okay, you want to disprove me? Come up with one experiment. Just one experiment that disproves it. Then my theory is gone. But not only show that the experiments show that Einstein's theory is correct. Einstein's intuition is right here, right? Okay. So Einstein said that since the equivalence principle is correct, that's his intuition. If you want to prove him wrong, come up with an experiment that shows that that is wrong. So what he said was the equivalence principle is correct. Its frame of reference sitting at rest in the gravitational field is exactly equivalent to a frame of reference accelerating the acceleration A. Right? So it means exactly the same thing should happen in what? In a gravitational field. So if you place a clock up there and a clock here on the ground, on the floor, then they must, the one which is closer to the one which is in the stronger gravitational field, the one closer to the surface. So the one in the stronger gravitational field, that clock will run slower. And now you see why in the interstellar, the stronger the gravity, the slower the clock, right? So it means you age slower near the surface of the Earth, but the difference is so small that you can, under normal circumstances, you can ignore it. So it means you will age faster if you are living on the third floor than you are living on the ground floor, right? Okay, but the difference is so teeny that in normal life you can ignore it. But it cannot be ignored if the gravitational field is let's say, as strong as the gravitational field of a black hole. Then the difference would be significant, right? Okay, so it means clocks run at different rates. Now comes the last part. How does this show that the space-time around a massive object, obviously space-time around a massive object means space-time in a gravitational field, is curved? Let's see. Now imagine that there is a clock up there in a gravitational field. Now we are in a gravitational field. Clock here, there's a tower, and there's a clock at the top of the tower, and the clock at the foot of the tower, right? Two clocks. And a light beam, this is not a rod, it's a light beam. This is a light beam, right? A light beam is sent from this clock to that clock. Right? The clock B, the clock A, a light beam. Okay. Now this is the this is the bottom of the light beam. Bottom of the light beam. Right? Bottom. And that's the top of the light beam. Okay. So let's say this light beam travels through the clock. Right? And a graph is graph is plotted of, normally we take time on the horizontal axis and x on the vertical axis, right? So this is what I'm going to do. Relativists don't do that. Relativists always have time on the vertical axis. and x here. But I'm not doing that at the moment. I'm just this is my distance move, right? And this is the time. Now this pulse, which I'm showing as this rectangular piece, this pulse travels through this clock, right? And starts moving upward. So let's say the top of this pulse leaves the clock at some time. Top of the pulse. Top of the pulse. At this time, the top of the pulse leaves this clock. And this top of the pulse travels to what? The other clock and enters this clock. So what will be the distance time graph for the top of the pulse?
Straight line.
It will be a straight line, yes. Until it crosses this clock, right? So, okay. And reaches here. So let's say that is this time. At this time, it is completely received by A, right? What will be the bottom of the pulse? Graph for the bottom of the pulse, same, but at a later time. So the bottom of the pulse will be sent at a later time. Same graph. Oh. Will be received at a later time, right? Are they parallel? Are they congruent, equal? Are they? They should be. There we go. Equal and parallel. According to flat geometry, if you have two equal curves or lines, parallel and equal, what do you say about this? If the geometry is flat, what do you say about this and this? It should be equal and parallel. What if they're not equal? What was the conclusion? It has its intrinsic curvature. Now, this is the time measured by what? Time measured by what? Who has measured this time?
Clock A.
Clock A.
Clock B, sorry.
Yeah, B. Clock B. Time measured by what? Are they same? Are they same? Are the clocks ticking at the same rate? Are the clocks ticking at the same rate? According to equivalence principle, the clocks are not ticking at the same rate. Which means what? They're not equal. So two sides congruent and parallel. These two sides not equal. What do you conclude? What do you conclude? That the space-time in the presence of gravity, you see, if there is gravity, the clocks won't tick at the same rate, just because of gravity. So if these two clocks are not ticking at the same rate, these two parallel equal, but these two won't be equal. And this happens when the space, or whatever the surface or space-time, is not flat, it's curved. So this clearly demonstrates, this was Einstein's line of reasoning, that if equivalence principle is correct, these two clocks won't run at the same rate. And if the two clocks won't run at the same rate, these two won't be equal. It means the space-time is curved, it has an intrinsic curvature. So it means in a gravitational field, obviously, where do we have gravitational field? In the presence of a mass, like Earth or Sun. But whenever you have Earth, Sun, and there is a gravitational field, the space-time around it cannot be flat. It has to be what? Curved. So, if a space-time is curved, how will objects move in it? Suppose, if the space-time is flat, or the space is flat, an object is trying to go as straight as possible in that flat space. Right? So, what will be the path? If the space is flat and object is trying to go as straight between 2 points, what will be the path? No, in a flat space. So if you're trying to go as straight as possible in a flat space, your path will be a straight line. But what if you're trying to go as straight on the surface of a sphere?
Curve.
It will be a curve, right? So it means even if you're trying to go as straight as possible in a curved space-time, your path won't be what? Won't be straight. So what Newton said was the moon is orbiting the Earth because Earth is applying a force on it, and that's why it's going around it. Earth is supplying the centripetal force. But Einstein saying what? No force, nothing. It's because the space-time around the Earth is curved. And moon is trying to go as straight as possible in a curved space-time. And ends up moving around the Earth because the space-time around the Earth is curved. No force, nothing, right? So, can you just show me a video for demonstration of curvature of space-time? Gravitation, curvature of space-time video. Curvature of space-time, gravitation video.
So if it's not a force, then why does it say the four in the four fundamental forces?
Okay. There we loosely say force. We should say interaction. Okay. If after this I'll tell you something really interesting.
Empty space, or actually empty space-time, as a rubber sheet, like a trampoline. A heavy object like the sun will actually bend the sheet, and the heavier it is, the more the sheet, space-time, is bent. And if you now roll a lighter object, say a planet, along the sheet in a straight line, the curvature of space-time will cause it to move in a circular path around the heavy object. The planet is actually following a straight line, but in curved space.
Yes, thank you. Now, one more interesting thing. Now you might say, if it's not a force, it causes objects to accelerate. If you drop an object, it accelerates down. And only a force can cause an object to accelerate. What's happening here? Can anyone figure out where we're going wrong in this line of reasoning? Don't objects accelerate down? So for gravitation causing objects to accelerate, and it's, only a force can cause objects to accelerate. So what's going wrong here? Something is wrong. Acceleration has to be, what we are talking about is a 3 acceleration. Acceleration has to be what? A 4 acceleration. So it means acceleration is not ax, ay, az, it's what? Ax, ay, az, at. So suppose if, now this is so surprising. According to Einstein's law, an object lying at rest in a gravitational field is actually accelerating. An object freely falling, has no acceleration. Provided we consider the 4 acceleration and not the 3 acceleration. Suppose if an object is lying at rest on the surface of the Earth or any planet or sun, etc. It has no ax, ay, az because it doesn't have any 3 acceleration, but it has an at, and there's nothing to cancel that out. So it means overall it has a 4 acceleration, but the magnitude of the 4 acceleration of the object won't be 0. It'll be non-zero. But what about a falling object? Remember I said that in every 4 vector, these come with one sign and the time component comes with an opposite sign. So when an object is dropped and there's no other force acting on it like air resistance or any electric force or any magnetic force, no non-gravitational force is acting on it. Only gravitation is acting if you consider it to be a force. It's not actually. So if you drop it, according to Einstein, it's isn't it a free particle? Because gravity is not a force, it's a curvature. It's a free particle. And free particles have 0 4 acceleration. The magnitude of 4 acceleration